So, in this video, we're going to just look at an example solution for a confidence interval and a hypothesis test for the difference in two population proportions. Alright, so here's the example. A national poll randomly selected people from two age ranges, younger people 18 to 45 and older people 46 to 80. To determine if they were coffee drinkers, each person was asked if they drank at least 1 cup of coffee per day. So that's their definition of a coffee drinker. The sample yielded the following results. 360 out of the 1,022 younger adults said they drank at least 1 cup of coffee per day, whereas 430 out of the 1,150 older adults said they drank at least 1 cup of coffee per day. Okay. Now, if you'd like to pause the video, go ahead and label and pull out the information for your info box. Now when you do that, hopefully you'll get this right here, that there's two populations, younger and older. The trait is a yes-no trait. It's whether you drink at least 1 cup of coffee per day or not. And then here's your sample information. The sample size for the older from the older population is 1150 or 1150 p hat. The sample proportion from the older population is 430 divided by 1150, which is 37.4%, but we always work as a decimal, 0.374. For the younger, the sample size was 1022, and the sample proportion from the younger population was 360 out of 1022, or 0.352, 35.2%. Okay. Now, what we want to do then is to find a 98% confidence interval for the difference in the proportion of older and younger coffee drinkers, and then write a sentence interpreting that conclusion based, of course, on the confidence interval that you get. Now, you should, of course, check conditions, so let's just run through that. The two groups, meaning the two populations, should be independent. And the coffee drinking habits of older and younger people are independent of each other. Random sampling was stated. The 10% condition, each of the sample sizes are less than 10% of all older people and all younger people respectively. Be careful not to say something like N sub O, right? The sample size of from the older population is 1150, which is less than 10% of all older people who drink coffee or who are coffee drinkers. Because once you put on that little qualifier, who drink coffee, you're saying that your population is only the yeses, okay? So let me just kind of make a little comment on that. It's kind of a common thing that sometimes happens. Your population is yeses plus no's, right? So you have somebody who's a coffee drinker, somebody who's not a coffee drinker, somebody who is, somebody who is, somebody who's not, somebody who's not, somebody who's not. If you say 10% of all people who drink, who are older and drink coffee, you're saying only the yeses, like you're not including the no's. So just be careful with that. That's a common thing that might happen. So your population is all older people or all younger people, then you have 10%. Your sample sizes are less than 10% of those populations. For your representative sample, you can just pull out from your info box, right? 430 and 360, respectively, 430 and 360, and then subtract from the sample sizes the yeses from the sample size to get the no's, the yeses of the younger from the sample size of the younger to get the no's. And remember, all you have to show is that there are at least, what, 10 of each, right? 10 yeses and 10 no's from both samples. All right, and then independent, one adult, it doesn't matter whether you're younger or older, who drinks coffee isn't going to affect whether another one does. I mean, even if one says, hey, this is great coffee, and one tries it, it's not going to make them a coffee drinker that drinks coffee every day unless that's actually who they are. So, you know, one isn't going to really affect the other. Now, let's take a look. After we've done conditions, we want to actually start our calculations. There's just a lot to this, isn't there? All right, so now let's go back to our question. We want to find a 98% confidence interval for the difference in the proportion of older and younger coffee drinkers. And let's not forget our info box here. Right? So I'll pull that back up. Our general structure is p hat older minus p hat younger, right? What's the difference in the sample proportions? And add or subtract the margin of error. Let's see here, that's standard error of p hat older minus p hat younger. Now a couple things here. Let's just remind you that from another video to know which standard error you use. It depends on whether you're doing a confidence interval or hypothesis test. If you're doing a confidence interval, then you'll want to use what I'll call the regular standard error, right? P hat 1, square root of p hat 1, 1 minus p hat 1 divided by n1 plus p hat 2, 1 minus p hat 2 over n2, right? Square root of all that. And so if we do that, I've already done that. For the confidence interval, you should get this. And you might want to pause the video and just see if you get the same thing. But 0.0206585. And also just another comment. I could have written this p hat old minus p hat young plus or minus z times standard error. This, what's inside here in these parentheses, is just the name of the standard error. It's telling you what am I taking the standard error of. I'm taking the standard error of the difference in the sample proportions for the old and the young, right? It's really just part of the name. You don't actually put in here 0.374 and 0.352. You don't do that. So remember, this is part of the name of the standard error, all right? So the actual standard error what you put in here is this. Right, so here's the standard error. I'm telling you this, I'm taking the standard error of this, and what that is this side. Everything on this side of the equal sign. So it's this square root, right? Everything that's under this square root. And this is the number you put in here. That's all. So let's go ahead and fill that part out. So from our info box, I have 0.374 minus 0.352. So 0.374 minus 0.352. Take that difference and add or subtract. Now the Z multiplier, we're looking for a 98% confidence. So I go to my T multiplier page. Here's 98% confidence. I look at in degrees of freedom of infinity, and I use 2.326. And then let me pull back this. 0.0206585. All right. Okay. So now, if I make this difference, I get about a 2.2% difference. Now keep it as a decimal. But what you're saying is there's about a 2.2% difference in the rate of the trait occurring in the two different populations. But we don't know, is that really a difference, or is this just a difference that's occurring because of sampling variability? Right? That's what we don't know yet. So then let's add or subtract our margin of error. We'll get 0.0480517. And when I go ahead and do this minus this number and this plus this number, I'll get a negative 0.0261 to a positive 0.0701. Right. So what just happened? Did we capture 0? That should be our question, right? If we capture 0, then what do we know? Well, here's how we know if we capture 0. We go from a negative to a positive number. So did we capture 0? Yes. We captured 0. So that means there's really no difference in the population proportions for the rate of the trait that the trait occurs. There's no difference because you captured 0. So the difference could be 0. If the difference could be 0, that means the two groups could be the same. So let's go back to, remember these papers that I'm pulling in here are from different videos. We looked at the conclusion and interpreting sentences. So is 0 in the interval? Yes, it is. So what do I write? I write with a blank confidence. In our case, we are doing a 98% confidence, right? So with a 98% confidence, the difference in the percent of, in this case, population 1 could be older and population 2 younger, who are coffee drinkers or who drink at least 1 cup of coffee a day, is between, and then you give me the percents, negative 2.6% to positive 7.0%. Right? And it doesn't matter if you'd set it up the other way, you would just say negative 7 to positive 2.6%. It doesn't matter. If you'd set it up young minus old, that's the only difference that you'd have. So here's your conclusion then. Right? With a 98% confidence, The difference in the percent of older and younger coffee drinkers understood that drink at least 1 cup of coffee a day is between negative 2.6 and positive 7.0%. Okay? All right. So then we're going to go to the hypothesis test. All right. And with a hypothesis test, you're asked to test the claim for the same problem so that we can see how they're similar, how the conclusions really are similar. They give you the same information. Test the claim that there's a greater proportion of older coffee drinkers than younger coffee drinkers at a 5% significance level. All right, so alpha is 5%. And they want you to test that there's a greater proportion of older coffee drinkers. So that's PO is greater than PY, right? And remember, not P hats. These are claims about the entire population. Okay? So, our info box still stays the same. We're going to use all that. And now, let's go ahead and start the process. We're going to do a hypothesis, right? Now, most likely, what you would say, most likely you would convert this by saying minus PY, right? And you'd get PO minus P sub O minus P sub Y is greater than 0. So that's what I'm going to go ahead and use. P sub O minus P sub Y equals 0. P sub O minus P sub Y is greater than 0, right? But this is the easiest way to translate it kind of directly. Now, technically we would go through conditions again. But we've already done those in the video, so you can just look back at this. The conditions are met. And then that allows us to create our model. Now remember, for our model, which standard error do we use? Well, you're going to use the pooled standard error. So let's take a look at which one that is. And again, you might want to pause the video. Right, so if you see, here's the information you'd need to be able to do the pooled. You could pause the video and see if you get, indeed, what we're about to get. Okay, so here we go. I've already done this for the hypothesis test. The pooled proportion would be about 36.4%. And then I put it in the equation, right? And I got, again, it's very close, but still you have to use this theoretically. All right, so we're going to use this. Now, what I'll say is that I'm going to kind of, even though technically it's really, there's a very long number, I'm going to round to 0.02 just so I can see what's going on. So what I mean by that, I'm going to say standard error pooled is approximately 0.02, and that's a real approximation. We're going to use that really long number for the z-score. But what I'm saying here is, remember, my null is at the center of my model. And then I add 0.02, add another 0.02, so 4.06, and here we subtract 0.02, 0.04, 0.06. Now, remember, this is 1 standard error, 2 standard errors, 3 standard errors, very approximated. -1 standard error, -2 standard errors, -3 standard errors. And what we've done is we want to test and see, with our test, what is the sample, the difference in the sample proportions. Well, that's 0.374 minus 0.352, right? Remember, that's right over here. 0.374 minus 3.352 for my info box. And that means I get a sample difference of 0.022. Now, where do you actually see that fall here? Well, 0.022 is just barely past 0.02. It's like very close to what? 1 standard deviation, just a tad bit more. And then, because I subtracted in the same order that I set up my hypothesis, right? O first and then Y, so O first and then Y. I can follow this and say, oh, okay, I can shade to the right. As long as you're consistent with your subtraction, you can do that. Use the direction of the alternative to know which way to shade. So now I'm saying, okay, how many standard errors away is this sample difference from my mean? So here's our z-score. P hat O minus P hat Y. Here's my sample difference. How far is that sample difference from 0 over the standard error that's pooled? Now, Now let's take a look at this theoretically. What I'm testing is not each individual sample, but the difference in the sample proportions. So that sample difference, I want to know how far is that sample difference from a difference of 0, right? A sample difference of 0, because I'm assuming the two populations are the same. So that's why I would say, okay, how far is 0.022 from 0 over, now I can use that really long, precise, pooled number, 0.0206840, and I'm going to get 1.063624. Right? Now does that seem about right? That sample difference really is about a little over 1 standard error, and that's what we saw. So this is why I use the model and then do an approximation, just to see is everything connecting correctly. Now what I'm going to do, I'm going to do normal CDF, right? I'm going to find the area under the curve here from 1.06364 or 3624, sorry, to 100, right, infinity, and I'll get about 14%, right? So we'll say 14% p-value. Okay. Now, that's a very high p-value. So the p-value for my conclusion, remember the p-value is here greater than the significant level alpha. Why? Because 14% is greater than 5%. So did my model predict what was going to happen at a high rate? Yes. The sample difference I got was close to the mean, so there was a high chance of getting that sample difference. My model did a great job of predicting what was going to happen, so I don't want to reject my model. So when I look at my null then, right, I do not reject null. Right, so I said this could be true. It's possible. So what's not likely to be true? The alternative. All right. So now, remember, I would want to say, what does my alternative say? Let's go back to probably this format right here. PO is greater than PY. Even though my alternative, actually I wrote it as the difference is positive. It's easier to translate this way. So remember, this is saying let's say percent of older coffee drinkers, or people who drink coffee, is greater than the percent of younger people who drink coffee, right? All right, so this is greater than, and this is the piece of wax. So I want to say do not reject the null, so therefore, if I'm not rejecting the null, I'm saying the null is possible, therefore what's not likely? This is not likely. And the way I say that is there's not enough evidence that, so I'll say there is not enough evidence that the percent of older people who drink coffee is greater than the percent of younger people who drink coffee. Ta-da! So that would be the end of your conclusion. And hopefully you can see the tie-in that you did not reject your null. Your null says that the difference is 0. And if we look back, if I can find it, we had captured 0 in our confidence interval. We captured 0. So honestly, if we'd done when we had done our confidence interval and we knew we captured 0, I already knew in advance that 0 was possible, so I was not going to reject the null. And therefore, there was not enough evidence for the alternative. So I wanted to show that tie-in because they're really two sides of the same coin, confidence intervals and hypothesis tests. If in your confidence interval you have captured in your interval what the claim for the null is, then you know you won't reject that null. Okay? And if you don't capture the claim that is the null, then you will reject the null. All right. Thanks so much for listening.